Welcome to this explainer. Today, we are looking at a highly targeted, incredibly effective strategy for tackling some of the most complex physics exams on the planet. Specifically, we're decoding exactly what Cambridge examiners want to see when they look at your answers for IGCSE Physics 0625 circuit questions. I want you to think of your exam preparation process like being a master sculptor. You start with this massive, intimidating block of raw physics concepts. It's heavy, it's unstructured, and quite frankly, it's overwhelming. But our goal today is to methodically chip away all the irrelevant material. We're going to remove all the fluff, all the generic textbook phrasing, and reveal the absolute masterpiece of an answer hidden inside that block. To really set the stage for why this matters, I want you to picture a tension-filled exam hall. The clock is ticking, the silence is deafening. On the desk in front of you is a classic, multi-part, highly complex past paper question. It features a potential divider, an NTC thermistor, and a relay, all wired together in a scenario you've never seen before. Now imagine two candidates sitting in that room. First, we have Alex. Now Alex works hard. Alex has memorized literally every textbook definition, but in his answer, he completely overloads the page with raw, disconnected physics facts. He's writing down Ohm's law, he's writing down the definition of resistance, he's practically writing the history of the battery. But he provides absolutely zero specific analysis of the actual circuit printed on the page in front of him. Then, a few desks down, we have Sam. Sam is entirely panicked by the ticking clock. Sam rushes. Because of that panic, Sam completely misses the crucial command words like analyze and deduce. Instead of breaking the problem down, Sam just scribbles down a single final number at the bottom of the page with absolutely no working shown. So what happens? When the examiner's red pen hits the paper, both of them lose massive marks. Alex gets penalized heavily for relevance because he didn't answer the specific question. Sam gets penalized for lack of method because he didn't show his working. Today we're going to explore exactly how you can avoid both of these exact problems and start claiming the top marks you actually deserve.
Okay, let's dive into this. Did you know that circuit diagrams and their associated components make up a staggering 15% of the total marks in this Cambridge physics examination? I really want you to stop and think about what that actually means for your final grade. We are not just talking about a couple of quick multiple-choice questions here. That 15% is massive. It is very often the exact difference between securing an A and dropping down to a C. It's the difference between missing your university target and securing your ultimate academic goal. Cambridge examiners dedicate a huge chunk of the paper to testing your knowledge on everything from power supplies, generators, and potential dividers, all the way to complex setups with thermistors, LDRs, relays, and LEDs. It is an incredibly dense, heavily weighted part of the syllabus. But here is the fascinating and honestly the most encouraging part. This 15% is highly predictable if you understand the underlying strategy the examiners use to build the questions.
So, here is exactly how we're going to break this down today. First, we'll look at the breadth of the 15% circuit challenge. Second, mastering core principles. Third, we'll explore the 5-step procedural framework. Fourth, we'll get into evaluative and critical analysis. And finally, we will reveal the top 3 examiner warnings.
Let's jump straight into Section 1, the 15% circuit challenge. Before we continue, subscribe to our YouTube channel Ace the Exams at acexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, looking at this breakdown on the screen, we have power and measurement tools clearly listed on the left and active and passive components mapped out on the right. Whether you're studying syllabus 0625, 0651, 0652, 5054, or even preparing for the jump to 9702 A-level physics, the vocabulary of physics is vast. Think of circuit symbols as the alphabet and the schematic diagrams as the sentences. If you don't know the alphabet completely fluently, you simply cannot write an essay. Candidates must know every single one of these components inside and out. But why is applying these components to unfamiliar contexts so incredibly challenging for most students? Because in a high-stakes exam, you won't just be asked to draw an LDR. That's too easy. You will be asked to explain exactly what happens to the reading on a voltmeter placed across a fixed resistor when the light shining on an LDR in the exact same series circuit suddenly decreases. You have to combine multiple components in your mind dynamically. If you only memorize them in strict isolation, your brain freezes when you see them working together in a live circuit.
That brings us right to Section 2, Mastering Core Circuit Principles.
The Cambridge assessment objectives deliberately target 3 distinct cognitive domains. Target 1 is knowledge and understanding. For example, can you simply identify a relay symbol on a page? Target 2 is application. Can you take a formula and calculate the current flowing through that specific relay coil? But Target 3, the one that separates the top tier from the rest, is analysis. Can you predict what happens to the secondary circuit if the primary coil's voltage suddenly fluctuates? To consistently hit these high-level targets, top students use an analytical structure called the PEAL framework: point, evidence, explanation, link. Let's do a quick mental exercise right now to see this strategy in action. I'm going to give you two answers, and I want you to spot the better one. Here's the scenario. A thermistor is heated in a series circuit. Answer A says, resistance goes down, so current goes up and the voltmeter reading changes. Now answer B says, as temperature increases, the NTC thermistor's resistance decreases, that's your point. According to V equals IR, for a constant supply voltage, total resistance drops, increasing total current, that's your evidence. Therefore, the fixed resistor takes a larger share of the potential difference, that's your explanation, increasing the voltmeter reading across it, and that's your link. If you recognize that answer B is the masterpiece, you're already seeing the incredible power of the PEAL framework in action.
This brings us to a massive realization. Top-performing students exhibit connected conceptual understanding that is completely transferable to unfamiliar contexts. Simply memorizing disconnected facts will not cut it anymore. Going back to our earlier example, Alex failed because he could not transfer his rote textbook knowledge of an NTC thermistor to a real-world fire alarm circuit diagram that he had never seen before. He just dumped data on the page. The real goal is to look at a tangled mess of wires and symbols, calmly isolate the core principles, like Kirchhoff's laws for current and voltage, and apply them directly to a totally novel situation. Let's be clear, examiners deliberately design circuits that you have never seen in your textbook. They do this on purpose to test this exact skill. They want to see your brain actively working, not your memory simply playing back a pre-recorded tape. We need to turn Alex's red pen marks into green check marks by forcing him to connect his facts to the reality of the diagram.
So how do we guarantee we can make those connections every single time? Let's move to Section 3, the 5-step procedural framework.
Let's see how this builds into a highly standardized sequence. This framework is the ultimate antidote to Sam's panic and Alex's rambling. Think of this as your physics success blueprint. Step 1. Deconstruct the question. Before you do any math, highlight the command word. Are they asking you to calculate, which means numbers are required, or are they asking you to suggest, which requires a logical proposition based on physics principles? Step 2. Extract relevant data. Physically write down V equals 12V, R1 equals 4 ohms, right next to the circuit diagram on your paper. Get it out of the paragraph and into your line of sight. Step 3. Select the analytical framework. Ask yourself, are we dealing with a series circuit rule here or a parallel circuit rule? Step 4. Execute with clear notation. This means you write the formula down first, you substitute the number second, and you calculate third. Never mix those up. And finally, Step 5. Present with correct terminology. Do not just write the number 6 at the bottom of the page. Write 6.0 amps. By applying these exact 5 steps religiously, you systematically build an impenetrable wall of logic that the examiner literally has to award marks to, even when you're under the intense pressure of a ticking clock.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's look at the most vital secret in Cambridge physics, the method mark strategy. Marks are awarded for the systematic process and clear working, not just the final numerical answer. Listen closely, because this is where Sam threw away his grade. If a calculation question is worth 4 marks, the final correct numerical answer might only be worth 1 single mark. The other 3 marks are awarded strictly for writing the correct formula, showing the correct substitution of values, and rearranging the equation correctly. If Sam rushes, punches a bunch of numbers into his calculator, and writes down the wrong final answer because his finger slipped on a button, he gets an absolute 0. But if you use the 5-step framework, write your working clearly, and make that exact same calculator typo, you walk away with 3 out of 4 marks. You literally guarantee partial marks just by documenting your thought process. It's a complete game changer for your exam strategy.
Let's step into Section 4, Evaluative and Critical Analysis. Here is the absolute timeline of thought a student must go through for critical analysis. It's an interactive workshop in your mind. Identify, break down, solve, check, and recommend. I want to do a quick interactive challenge with you right now called Find the Flaw. Listen carefully to this sample paragraph that a student wrote in a past exam. The circuit has a 12-volt battery and 2 6-ohm resistors in series. Therefore, the total resistance is 12 ohms. The current is 12 divided by 12, which is 1 amp. The voltage across one resistor is 12 volts. Okay, your 60-second mental timer is running. Did you catch the critical flaw in that logic? The flaw is that final sentence.
The student systematically solved for the total current perfectly, but they completely failed step 4, checking for reasonableness. In a series circuit, the voltage drops across the components. A single resistor and an identical pair simply cannot take the full 12 V of the supply. The correct voltage across one resistor is 6 volts. Finding these exact types of logical flaws in your own working before the examiner does is exactly how you secure those top grades. Top-scoring candidates demonstrate evaluative thinking exactly like that every time they sit down. They question assumptions, they consider different perspectives, and they justify their decisions with hard evidence. Let's do another quick challenge: speed writing. Imagine you only have 30 seconds left on the clock to write a perfect paragraph explaining why adding more identical lamps in parallel doesn't dim the existing lamps. You'd need to formulate this peel structure instantly in your head. Point: the brightness of the existing lamps remains the exact same. Evidence: in a parallel circuit, the potential difference across each individual branch is always equal to the source voltage. Explanation: therefore, the current flowing through the original lamp remains completely unchanged because both V and R are constant. Link: thus, its power output, and consequently its brightness, are unaffected. Boom! That is exactly how you extract maximum marks in minimum time.
Finally, we reach Section 5, the top 3 examiner warnings, pulled straight from the official Cambridge Principal Examiner reports.
Treat this slide as the ultimate trap you need to avoid. The examiner report states, the classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario. Remember Alex from the very beginning of our explainer? This is the exact trap he fell into. He wrote down everything he possibly knew about electromagnetic induction when looking at a diagram of a transformer. But he never actually mentioned the specific number of turns on the primary and secondary coils that were literally printed in the diagram right next to the question. If the question gives you a specific context, say a motor lifting a 5-kilogram mass, your answer must specifically reference that exact motor and that exact 5-kilogram mass. It absolutely cannot just be a generic textbook definition of how a motor works.
Let's clearly break down the top 3 specific mistakes students make when drawing or analyzing circuits. Warning 1: answers are simply too vague. Saying something like, the current changes, will get you 0 marks. Saying the current increases from 2.0 amps to 4.0 amps gets you the mark. Precision is everything. Warning 2: students completely forget to check their format and presentation. Drawing a circuit diagram with tiny gaps in the connecting wires, or drawing a wire line straight through a voltmeter symbol will lose you marks instantly. Use a ruler, use a sharp pencil, and make your diagrams flawlessly precise. Warning 3: as we just discussed, answers are not specific to the context. This slide right here is essentially your final, non-negotiable checklist before handing in that exam paper.
Here is the ultimate contrast you must understand: generic versus specific. Generic is writing down a memorized definition of a thermistor without even looking at the rest of the circuit diagram. Specific is actively analyzing how that NTC thermistor interacts with a potential divider in the exact, unique scenario provided on the page. When you make the mental shift from generic memorization to specific application, your mark potential dramatically increases to 100% because you are finally answering the specific question the examiner actually asked rather than the easy one you wished they had asked. Now, students who implement these physics strategies see an average improvement of 2 grade boundaries, but that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexamsIGCSE and click that bell. Don't let another exam pass you by.
So, I want to leave you with this provocative thought to really chew on before your next study session. Are you just memorizing facts like Alex, just hoping the exact textbook example magically shows up on the exam paper? Or are you finally ready to adopt the 5-step framework, systematically evaluate your next complex circuit scenario, and stop losing easy marks? It's time to take control of how you evaluate information. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.